Greetings. I am Parthopatim Roy, and today I am going to present my final project of the course ME 7751, which is Computational Fluid Mechanics, and the title of the final project is Flow Through a 2D Stepped Channel. Here are the contents that will be described in the following presentation slides. Here is the objective of my present work, but the main objective is to learn how to make a simulation of flow solver for a geometry that is not the typical rectangular or square one. So here is the geometry and the boundary condition for my cases, and I will be considering two cases. One case there will be one step and only one step in the inlet boundary, and for the second case there will be two steps, one in the inlet and an outlet boundary. For the inlet there will be inter boundary condition, and for the outlet there will be outer boundary condition, and for both of the top and bottommost are at the no slip condition. The aspect ratio for both of these cases are set as 10, and for both steps, for either steps, the height of the step is considered as 0.5 times the height of the whole domain, and for the step length it is considered as the 0.1 for 0.1 times the length of the whole rectangular domain. Here are the Navier-Stokes momentum and the continuity equation that the fluid actually follows, and I'll be discussing these equations with central difference scheme as a special discretization method, and the Euler explicit method for the temporal discretization. So for the fluid flow simulation solver, I use the staggered grid compared to the collocated grid arrangement, and because it actually helps to implement the boundary condition along the boundaries, and it actually stabilizes the simulation solver. So here is actually the numerical solution step described in here. So to make it short, I first use the momentum equation, solve the momentum equation to get the value of u velocity and the v velocity, and then I calculate the divergence with the present u and v velocity, and then calculated the pressure, solve the pressure constant equation to get the pressure correction term, and then update the pressure, and then finally update the u velocity and v velocity so that it reaches it can satisfy the continuity equation, and then repeat the same process until the flow actually reaches the stage step. So for the validation, I am considering a simple rectangular channel where fluid will come through from the left side and go through to the right side, and both top and bottom wall is at a no slip condition. And this is similar to the case for the Hazen-Pascual equation, and the result of this simulation is described in the next slide. So for the simulation case similar to the Hazen-Pascual scenario, the fluid actually enters from the left and exits from the right side, and in this process actually there is a boundary layer at both top and bottom edge of the fluid domain, and the fluid becomes fully developed, and the fully developed U velocity profile actually looks as the parabolic profile, which actually conforms to the Hazen-Pascual equation. This is the result for the step one, and as you can see at the edge of the step, the fluid becomes fully developed for lower Reynolds number, but that is not the case for the higher Reynolds number. And also the vortex is being generated at the end of the step near the first step, but that vortex size actually increases with the increase of the Reynolds number. And from this velocity profile plot, we can see that there is a possibility of another vortex being formed near the top edge if the Reynolds number is increased to a necessary higher. So this is the result for the second case where there will be two steps, and as similar to the first one, the fluid becomes fully developed for a high lower Reynolds number, but compared to the higher Reynolds number at the edge of the first step. And also there is a vortex generated at the edge of both steps, but that vortex size is different. The vortex size actually is bigger for the first step and compared to the second step, and the vortex size actually increases with the increasing of the Reynolds number. And similar to the case one, there is a possibility of another vortex being formed near the top edge if the Reynolds number is increased at a higher value. Finally, these are the conclusions, and the most importantly, the case to the solution takes longer amount of time because there are two steps, and the fluid flow takes a little bit longer amount of time for it to reach steady state. With this, I conclude my presentation. Thank you, everyone.